Okay, right, we have the camera set up now, so I'll continue. Welcome to Rust 101. Hope you're all as excited as I am to be here. Can I get a show of hands of who actually has looked at a little bit of Rust, maybe has some familiarity with Rust? And who is a total beginner? Okay, good. All right, so for those of you who might not be entirely convinced, I'm going to talk about why Rust. And I'm going to attempt to convince you that in any problem domain that you might have, Rust should be an approach, a programming language that you consider to solve your problem. So first things first, I think the biggest thing is that it makes you feel like a genius. There has never been a time where I have programmed in Rust that I haven't felt like things are going super smoothly. Very rarely do you find that you are as productive in a language like Rust in any other language that you might think of. I'll talk a little bit about why that's the case. So one of the first things that you'll find when you open the Rust book, that's a book online that you'll find, is that Rust is about empowerment. It's about reducing your barrier to access to building software in domains that either you might be an expert in or you might be a complete beginner in. So if we consider things like operating systems, concurrency, and fields of software that seem like they're only sort of like reserved for wizards and people who are trained in these arcane sort of dark arts, Rust is meant to help you build software that will be industry standards and just work from the get-go. The compiler hosts a suite of tools to eliminate these common pitfalls. We'll talk about these pitfalls later. And the language naturally guides you to reliable, correct, and pretty beautiful code. It's expressive enough to build software in any domain, and I mean any domain. Practically any domain that comes to your mind, no matter how sort of far-fetched it might be, Rust is now mature enough that it could probably build software in that domain you're thinking of. It's also been voted most loved language for the last 7 years. I think that says something. So, most important thing is when you push your code to production, it should just work. Preferably, it should work, it should never crash, it should never have any bugs. Your client should be happy, your users should be happy, everything should just work. Rust is a language that aims to get as close as possible to that. There's something within Rust called the borrow checker, and it understands the way memory works in your application. Using that understanding, it promises you, so long as you stay within the realm of safe Rust, that your program is memory safe, which means you'll never have certain memory bugs like use after free or memory leaks, and it should be race condition free, meaning if you have multiple threads and shared resources between those threads, you'll never enter a corrupted state that you never imagined would happen in the first place. Rust is industry ready and present in many code bases today. There are 4 logos that you hopefully recognize. There is Rust in some significant code bases that these companies have built. And this is a non-exhaustive list. I think one that I want to talk about is Cloudflare and their project Pingora. Cloudflare are a company which I suppose power most of the internet today. They run a reverse proxy that handles about 1 trillion requests per day. It's 1 trillion, like 12 zeros. And they used to run a piece of software, if you happen to have heard about it, called Nginx. That's an industry standard off-the-shelf reverse proxy. And at some point, Cloudflare grew big enough that Nginx just was not, I suppose, suited to their specification requirements. So they decided to build their own reverse proxy. And to this day, it's handled a couple of 100 trillion requests ever since it's been brought into production. And it's never crashed once. In fact, it is so bug-free that the only times Pingora has gone down has been because of hardware-related bugs or kernel bugs. The software itself is watertight. and that can be attributed to the fact that it is written in Rust. Another thing I want to talk about, which I briefly talked about earlier, was fearless concurrency. Any of you who have happened to work with concurrency in the past know that concurrency bugs are some of the most awful bugs to debug. Rust promises you that a good sort of subset of these concurrency bugs will never happen in your program. Namely, that your program should be race condition free. There are simple constraints on how memory in your program is meant to interact with the rest of your program. And the borrow checker verifies these constraints. And once these constraints have been verified, the borrow checker will promise you that you no longer have these race conditions in your program. There are well-designed concurrency primitives, so you don't have to go through a lot of hassle to get things like locks in your program. And libraries like Rayon, and we'll get to this in hopefully some of the more future sessions, make parallelizing your program super easy. It's a case of maybe changing 1 or 2 lines of code to get your program from sequential to parallel. And it's as easy as that. Concurrency, point is, becomes super simple in Rust as well. Rust is also super fast. Has a suite of super optimized data structures that just work. It is not garbage collected like some other languages you might be used to, like Python or Java. Let me get my notes here. There's something called monomorphization that is sort of, I suppose, a feature of the Rust compiler. And what this means is when you write generic code, the compiler will build essentially concrete versions of that generic code for each type that it's applied to. What this means is Rust is able to optimize your code, generic code, specifically for the types that it's applied to directly. So suppose you operate on you have a generic function, you apply it to a list, and later you apply it to a hash map. Rust knows to optimize these separately and optimize them in context of the specific type that it's working with. Its speed, it's the same old LLVM backend. For those of you who aren't familiar what LLVM is, it happens to be sort of the last stage of compilation. Once you've built some sort of intermediate representation with the compiler and you're generating the assembly at the end, this is what LLVM does. And LLVM happens to power a lot of languages today, like C and C++. And Rust works with that same backend too. My point is, a lot of the time, Rust will compile down to the exact same assembly that an equivalent C program would. Rust otherwise will come to about 10% of the speed of a C program. And it means that you get code which is clean, well abstracted, and maintainable without taking any performance hits for the abstractions that Rust provides for you within your programs. Point is, you get to write code that is objectively better and not have any downsides for it. Final thing I'll touch on, and very briefly, is seamless interoperability. For those of you who might happen to work on established code bases already that are in C or C++, and you're thinking, God, I want to write this new feature in Rust. How am I going to do that? They will interoperate completely seamlessly. Rust doesn't have a garbage collector, which means there is no setup to have it interoperate with C. And software today uses Rust code in other languages like Python, C, C++, Go, Haskell, C#, and so on and so forth. So you can insert Rust into already established code bases, headache-free. So hopefully by now you're convinced. What now? Well, we're here to learn Rust. And the objective is that we will hopefully end this session with you able to go home and write your own programs, even if you've come in here as a total beginner. So we'll take a brief tour of Rust. Taking a brief tour of Rust means I'll go pretty fast. If I happen to be going too fast, if anybody happens to have any questions, feel free to stop me at any time. This symbol here is an important one. This will show up anytime I show you code that does not compile. And anytime you see this on the next slide, you'll also see one of the beautiful error messages that the Rust compiler comes up for this code. Let's begin. This is a let binding. This is how you declare variables in Rust. Let, variable name, and the data on the right-hand side. You can give a type to a variable using this syntax. That here we have a variable nickels, and we're assigning it the type of an unsigned 32-bit integer. We can annotate types like this. We can annotate variables like this. This is a variable named nickels. We've annotated it with a type, unsigned 32-bit integer, and we've assigned it later. This is separating it onto 2 lines. One of the key things that I want to note is this idea of unsigned 32-bit integer. If anybody happens to be coming from a high-level language where we just think of integer, you might be stuck on thinking, okay, what sort of number type should I use? In general, default to using this one. This means signed 32-bit integer. This is what Rust will also default to as well, if it ever happens to find any ambiguities with your numbers. This is an uninitialized variable. Note the warning sign. This will not compile. Reason for it is we have a variable there, we've annotated its type, however we haven't initialized it. This is very, very dangerous. However, it's acceptable in a number of other languages. So for example, C, if you happen to have uninitialized variables in C, you can use them freely like this, and you'll end up getting what's called undefined behavior. Inside this variable, there could be, when it's uninitialized, there could be any data randomly put in there in the compiler until you initialize it at first. So using it like this is dangerous, and Rust forces you to initialize a variable before you use it. Hopefully, this is, you guys can see that at the back? Yeah? Okay. So this is one of Rust's pretty amazing error messages. I think the most common thing I tell people when I talk to people about sort of like an introduction to Rust is read the full error message. We as programmers have been trained to read the first line of the error message, throw it into Google, and cross our fingers and hope for the best. In Rust, the answers are already there. If you just read the full error message, the compiler will tell you how to write your code properly. And in this case, it's telling us that we have a binding that is uninitialized, and it tells us that we use it when it's uninitialized. And it also happens to have this command here, if we happen to be still unsure, where it'll take you to a part of the Rust documentation explaining to you the different common ways you can find yourself in this error and how to resolve them. This is how we would resolve it. We would have the binding type, and then we initialize it first, and then we'll use it. Sometimes we have unused variables, and we have a genuine reason for having unused variables. The Rust compiler doesn't like this, so it will warn you about it. However, if you use an underscore in place of that variable name, Rust will take it that this is an unused variable, and will be happy with it. Tuples are pairs, pairs are tuples. Hopefully you guys are familiar with this from other languages that you've seen. Pairs can have multiple types. They don't need to be homogeneous. And we can access these different parts of the pair using these 0 and 1 attributes. We can destructure pairs, as you see up there. So we've defined a pair, and below we've destructured the pair into different variables. At the bottom, we'll see that we've destructured it. However, the first one we've left unused. This is one of the many common sort of like usages for this underscore. Statements are separated by a semicolon. If you have multiple statements, you'll separate them by a semicolon, have them on multiple lines. So this is kind of important because it means that we can have multi-line statements. That's not a problem. So this is one statement as a whole, Briefly, this is taking all numbers from 1 to 100, multiplying them by 3, adding 1, and then summing them. But we have this on multiple lines for aesthetic reasons, and we can do that because semicolons. This is a function. We denote functions with fn, the variable name, brackets, and then the function body. We can return values from functions. Note the arrow I32. That means that this function returns an I32. And here's a key thing. There's no return keyword, is there? That's because almost everything in Rust is an expression. Expressions are values. And so when we have this number 4 here, it is effectively saying, here's an expression with the number 4, surrounded by these curly braces, which is a block. So this will return the number 4. This is implicit return syntax. We'll get back to how we can do this explicitly too. Blocks denote a new scope. So we have a let binding up there assigning the letter x to 4. We define a new block using these curly braces, and that defines a new variable scope. Scopes are hopefully familiar to us from other languages. Within a different block, we can define the same variable and give it a different value. And this binding x will shadow the binding at the top. This means that once we've set this binding x to shadowing, we no longer have access to the x equals 4 at the top. However, we can reuse this name in this inner scope and print out that value x here, which should print out shadowing. And once we leave that block, x is 4 again. Yeah?
In the previous slide, if I do not have the let in the scope, then what is that?
So if you didn't have let x equal shadowing and you just did x equal shadowing, you would be using the variable in the parent scope. So you'd get a type error at that point because you're assigning a string to something that is an integer, a number. So you'd be essentially trying to modify something that is in the variable scope. So there are two things at play here. First of all, mutability, we'll get into that later. And second of all, type issues. But yeah, you would still be operating with the x in the parent scope. Blocks are also expressions. So these things with curly braces, they're also expressions. They return values. They have values. So these two statements are identical. Blocks can have statements inside of them, semicolons. And then we have the tail of the statement, because if you have a series of statements, these can also be an expression too. So they can also have a value. And this tail of the statement, you'll note that it doesn't have a semicolon at the end. That means this series of statements will have the value y plus z. And that means that this block will have the value y plus z. So at the end, we will bind x to the value y plus z. Back to explicit return syntax, these two functions are identical. So yes, Rust does have a way to explicitly return values, but the bottom one is cleaner, and generally, you should try to write your code to have implicit return syntax where possible. If statements are also expressions, so if our random number generator happens to be rigged, it'll return a 0, otherwise it'll return a 4. This if statement is in and of itself an expression, so it will take on a value, either 0 or 4, and this function will then return either 0 or 4 later. Match statements are also expressions. This is, I suppose, the closest thing that is in Rust to a switch statement. This is identical to the last slide, just, I suppose, a more concise syntax. Attributes and methods are hopefully familiar to us from other languages. So we have a pair, and we access it using the attribute 0. And at the bottom, we have a message, and we call a method on that message. We take its length, and hopefully we'll return 16 from that. This dot is how we access attributes and methods. Namespaces are a little different, however, because to go inside namespaces, we use this double colon operator. Namespaces, I suppose, are collections of functions. Namespaces can also contain other namespaces, hence the nesting here. Here, stud.min, you can sort of think of this as module file function. Stud being the Rust standard library, comp being the file, and min being the function. Here we're taking the minimum of 3 and 8. We can use namespaces using the use. Oh, yeah, go on.
Can we go to the previous one?
Absolutely.
One more.
One more.
Yeah, so here we have a.0, but can we have nested tuples so that will look like a.0.0?
Absolutely, yes.
So the compiler won't confuse it with a.0.0, which is floating.
How do you mean, sorry?
Sorry, so if we have nested tuple, so we're gonna have something like a.0.0.
Yes, absolutely, yeah. Yeah.
So yeah, that kind of look like a dot a floating point.
I wouldn't be able to tell you whether you need to bracket the a.0 or not as of now. You can definitely test that later. But you can have nested tuples and you'll access them with some variant of .0.0, whether that initial .0 is bracketed or not. So, using the use keyword, we can bring a namespace into scope. Once we brought a namespace into scope, we can refer to that function directly. Here we're again taking the minimum of 3 and 8. This slide and the last slide are identical. We can import entire namespaces using the asterisk. This imports every function that happens to exist in this namespace. Where did that come from? Yeah.
Yeah, is it good practice to have the use, or is it just that?
Good question. So generally you'll want to bring namespaces into scope where you can. If these namespaces happen to bring into scope functions with identical names or namespaces with identical names, you will want to use sort of like the full namespace path when you're referring to that function. Okay. Types also are namespaces, types being integers, strings, characters, etc. Here we have the first line should be pretty familiar to us. We're taking the length of this string. Here, string str is being used as a type, and that type also acts as a namespace. And when we do the double colon operator to get the length function, this is identical to the line above it. Some non-primitives are in scope by default. This is the vec non-primitive. This is essentially Rust's dynamic array. These two lines are identical and they will work in sort of like any Rust file. The only difference between them is that the top one uses vec directly with no namespace imports, and the bottom one uses the full path to vec. So back to your question over there, the top line is what would be best practice. The bottom line would be unnecessarily confusing. The reason why this works, by the way, is because during compilation, you'll never see this, but during compilation, the Rust compiler will insert this at the top of all your files. And this will contain all of these non-primitives that you'll use, like vec, box, option, result. We'll get into what those mean later. But this is automatically done for you, and those are brought into scopes. Match statements are concise control flow, so no weird if, else if chains. Just use a match statement. Here we're matching on the number 1, 2, 3. If n happens to match one of these things on the left-hand side, we will execute the corresponding thing on the right-hand side. This underscore is a catch-all. That means if it doesn't happen to match any of these on the left-hand side, it will default to the one with the underscore. Structures combine data into one record. This is a coordinate structure. We have an x, which is a floating point number, a y, which is also a floating point number. Structures are super easy to initialize. This is the syntax for initializing a coordinate. Values 2.5 and 3.5. And for those of you who might have a JavaScript background, this should seem really familiar. This is shorthand initialization of a structure. This double dot operator should seem similar to the JavaScript spread operator. The idea is this somewhere, we will essentially take the values of somewhere up there and use them to initialize elsewhere. So somewhere has the values 2.5, 3.5. Elsewhere has the values 10.3, and it will borrow the y from somewhere. It will take the value 3.5.
Somewhere has to be of type coordinate?
Yes, absolutely. The reason why I don't have type hints over here is because the Rust compiler is smart enough to infer the types for these. There will be occasionally points where you need to specify the type directly, but yes, they have to match types because of essentially Rust being a strongly typed language, yeah. There is a wrong way to use shorthand, and it's like this. And the reason for this is whenever you use shorthand to essentially borrow the attributes from one struct into another struct, it should never be followed by a comma. It should never be followed by more attributes. Look at this error message. Tells us there shouldn't be a comma here. Remove this comma. Base struct must always be the last field. I mean, it tells us how to fix our code. There is no more cryptic errors, cryptic error numbers, go throw it into Google and hope you find a Stack Overflow answer that will solve your problem. It tells you how to fix your code. Structures can be deconstructed, similar to pairs. Here we have coordinate defined up there. We give it some values, and later we destructure it into bindings x and y. This is a form of pattern matching, for those of you who have heard the term. Pattern matching is one of the most powerful features, I think, that Rust has. Deconstruction can also discard attributes. We see the double dot operator again, but this time it means something different. Here we destructure the x value, so now we've bound the x value in coordinates to that variable x. However, all of the other ones we've discarded. We don't care about those. This one might be a little bit tricky, but once you get it, you'll never forget it. Let statements can be conditions in an if statement. What this means is we can pattern match inside an if statement condition. So coordinate is being pattern matched out, and we're saying let's grab the y value from coordinate, and here we're matching on x being the value 3. So what we're saying here is if the value for x in coordinate is 3, then we will take the true branch of this if statement. If it's false, so if we don't have an x value that is 3, then we'll take the false branch of this if statement. The y value is what we're pattern matching out here, so this doesn't have any constraints on it. It'll only have a constraint if we specify the value to be pattern matched on. Sometimes. However, occasionally this can be cleaner, especially so later. I think this will make more sense when we go into options later. There's a really nice implementation of Dijkstra's algorithm in Rust that uses this, and it's very, very clean.
Can I use this x and y outside this if scope?
No. This x and y here are bound to the scope of the if statement, and in the so they're bound to the scope of the if statement here. Yeah, go on.
Can you use similar pattern matching like this in the match statements?
Yes, absolutely. We'll see that later.
If y is defined earlier, then is y shadowed here?
Yes, y is shadowed, exactly, yeah.
Can I use x in else branch?
That's a good question. I believe these are only pattern matched and bound inside this true branch. So in this false branch, x and y won't be accessible.
But y is accessible.
How do you mean, sorry?
So y is accessible here.
Oh, sorry. No, sorry. Where is my mind?
Maybe we can try out.
Yeah, no, well, I'll show you this later, but yeah, they are accessible in both branches, sorry. That's my bad.
Now, why is it beneficial here to say x cons 3 rather than just 3?
What do you mean, sorry? So do you mean checking whether coordinate.x is equal to 3 or checking?
Why define when writing a coordinate, what is the benefit of writing in Rust like x colon 3 and comma y rather than just saying 3 comma y?
Because Rust won't know. If we had more attributes, Rust won't know what you're referring to. So if we had a z component of this coordinate, then if we just said 3.0, 5.0 y, then Rust wouldn't know whether the 3.0 is meant to be pattern matched on the x or the z. Hopefully that makes sense.
And also for the dot somewhere kind of example, this would work.
Yes, this would work. So if we had x colon 3.0 and then dot dot, this would work, yes. Same thing can happen in match statements, so we can pattern match in the same way in match statements. Here, the left-hand side, pattern matching, and we use those variables inside this right-hand side block. Otherwise, there's the catch-all underscore, and there's what we'll execute if we end up in that catch-all. One of the important things with match statements that are kind of, they sometimes make using if-let more convenient than using match statements, is the fact that match arms must be exhaustive. So if we compare this with the last one, we'll notice that in this one, we're missing that catch-all underscore case. Here, Rust will complain. I'm hoping you guys can see that error at the back as well, right? Okay. It's telling us here that there's a specific pattern up there, which is coordinate dot dot, that we haven't covered. This essentially means we have a coordinate and we'll discard anything inside. This is equivalent to the underscore. Is that visible there? Yeah, it is, okay. It says coordinates defined here, and then it also shows us these match arms, and in green, it shows us what it wants us to put in our code. This is an example of a Rust error message where the compiler literally gives you something to copy-paste inside your program to fix it. So if we listen to the compiler and do that, this will compile. This is essentially saying coordinate, discard anything inside of it, which is a catch-all case for all coordinates. And on the right-hand side, there's this to-do. We'll get into that later, but that essentially means we will fill in that right-hand side in the future. Types can have functions implemented for them. We have a number structure, has a value, it has a, whether it's prime or not. And we have this impl keyword. This is called an implementation block. And this is us defining methods on a specific type. This is a function, it takes as its argument, its first argument, self. This might seem familiar to those of you who come from a Python background or from a Java background, or any object-oriented background for that matter. And this function will return a Boolean to see whether the number is even. We can use it like this, which is back to us using a method on a type. And this will print out whether this number 4 is even. Hopefully it will print out true. Yeah?
Are structs objects, or does it come like from Haskell background where we are defining data types and
Good question. Both. So I say both. Why? Structures are essentially records of data. So in Haskell, you have this idea of a product type, which is you'll have a data type defined, and you'll have the name of this sort of like data type and then the different types that it'll take. This is a product type. This idea of a struct is essentially the Rust equivalent of that. At the same time, this struct, when you go into the really low-level details, looks not exactly the same, but kind of similar to what a C struct would look like, or what a Java object, its data might look like in memory. For those of you from a Haskell background, type classes are very cool. Traits are like type classes. They're essentially the same thing. Anything that happens to implement a trait must implement the functions inside that trait. We can see this here. Here's our trait parity. And we implement parity for number. And when we implement parity, meaning number has the trait parity, we must implement all of the functions that this trait has. So in this case, there's only one function. We'll implement isEven and return a Boolean from that function. We'll get into some of the nitty-gritty details about traits in this lecture. This will be the most difficult part. We can implement foreign traits on our own types. What does this mean? If we have a trait that we've imported from an external module, we call those crates in Rust. So if we've imported it from an external crate, then we can implement that trait on our own types. Own type, meaning this type is defined in our crate, the project we're working on. So this is what we've done here. We've implemented stdops neg. This is overloading the minus operator for number. And what we return is we return, whenever we do the minus operation on something that happens to be of number type, we return that value negated. We can implement our own traits, like parity, for a foreign trait, like i32. i32 comes from the standard library, so we can implement parity for i32, and we can implement our isEven function for i32s. However, and here's the catch, we can't implement foreign traits on foreign types. This is something you may go many months in Rust without encountering, or it may be your first week in Rust and you'll hit this head on. But point is, this is not allowed. And this comes from a concept called orphan rules in Rust. We'll go into those a little bit deeper in future lectures, hopefully. However, the vague reasoning for this is we're avoiding dependency hell. If we have a trait that comes from one crate, a type that comes from another crate, if we're having the implementation in a third crate, that seems slightly insane. We should either have the implementation in the crate with the type or the crate with the trait. If we allowed this, it gets very messy very quickly. If you have multiple crates, one crate might have an implementation, one crate might have a type. If you drop one crate, you lose the implementation while still having the trait or the type, and basically any other permutation of that situation. So here's the error message that comes up. Essentially says what I was talking about over there. Only traits defined in the current crate can be implemented for types defined outside of the crate. So it says here, stdops neg comes from outside our current crate. Vec comes from outside our current crate, and it tells us to either define our own trait or our own type instead. This would be a error message that this part here would be very useful for, because this is kind of one of those errors that's a little bit difficult to wrap your head around. And hopefully I'll demonstrate that in a future lecture, and we can go into those docs together. Those of you coming from a functional programming background will be pleased by this. Rust is immutable by default. When we have a let binding, these variables are immutable. You can't assign to them later. That's what the Rust error message tells us here. So It tells us the first assignment to immutable is there. The second assignment is there, and we can't assign twice to an immutable variable. It tells us, however, how to fix this. Rust has opt-in mutability rather than opt-out. Rust's immutability is there as a core feature rather than having immutability as an afterthought with keywords like const. Here, once we have the mute keyword after the let, we can reassign this variable later. Functions can be generic. That means that they can be parameterized by a type. This is the identity function. Functions can be generic in multiple types. And functions, their generics can be constrained by a trait. If you think back to Haskell, this is like having a type class constraint on a polymorphic type. Structures can also be generic. We've redefined the tuple here just in a slightly different way. Vectors, structure we talked about earlier, are also generic. This means that we can define a new vector with exactly the same syntax, but push different things into it. And Rust will infer that v is a vector of integers and w is a vector of booleans. Vecs have literal-like definitions. So when you define an array literal in a programming language, this is how you would do it in Rust. This is a sort of like really interesting syntax because you have vec and then a bang later after it. You'll also have seen that with print statements as well. They're macros. And macros are essentially a form of metaprogramming, programming to do more programming. Macros expand into other code. Now, you may have seen this sort of macro in different languages before. If anybody has seen C, you will have seen the macro system in C. The Rust macro system is different. C's macro system is kind of like a templating system more than anything else. It tends to result in weird error messages, bugs, and it generally looks horrible. So most languages have learnt the lesson that macros are bad. JavaScript learned this, Python learned this, Java learned this. Rust says no, macros can be good. And Rust's macros take from Lisp metaprogramming. Lisp's metaprogramming, for any of you who may have seen it, are essentially the golden standard for macros in any programming language today. And Rust has a very similar macro system. Print line, as I was talking about earlier, is a macro. When you print, that's what it gets expanded to. It's much easier to stick with the top one. Panics are also a macro. These violently stop execution anytime the code hits a panic. This is maybe the closest thing you'll get to a runtime error in Rust. This is what a panic looks like. So this is what running the code that we just saw on the last slide looks like. Thread main panicked, and there's your error message. And panics will also give you the file, line, and column that this panic originated from. Methods may panic as well. So a lot of you are familiar with maybes or option types. This is an option in Rust. And at the top one, we've defined an option with some value. We unwrap it, we print it, and that print statement should print 3 later. The bottom one, we have an option that is empty. And as soon as we unwrap that, our program should panic. I refer a lot back to Haskell here. So if anybody doesn't have a strong Haskell background, feel free to ask me any questions about what I'm talking about. But the Haskell from just function is like an unwrap. This is what that looks like. So I said we'd print 3, and then the second one would panic. And it says we called unwrap on a non-value. There's our file, line number, and column again. Options are interesting. because they're not structures, they're enums. Enums in Rust are quite powerful. Here we have two variants, none and some. None meaning this option is empty, some with the generic type T meaning this sum can contain anything. And this is the implementation for unwrap on this enum. We'll match on self, and if we get a sum, we'll return T. If not, we'll panic. I want to focus specifically on this part. This is matching on an enum again. So we can match on the different variants on the left-hand side, and on the right-hand side, we'll have the execution if we happen to match on those variants. Result is also an enum. We have an OK variant with the data that it'll have. And then rather than having the none variant, we have an error variant with an error type inside of it. We can match on results. So this is us reading from a file to a string. We can match on that file data. If we happen to have gotten data from that function, we'll do something with it. Otherwise, we'll print that we couldn't read file, got error, duh. And the program continues. This is great. No more are exceptions that get thrown like Java, which was a horrible way of doing things, and the try-catch mess that ends up with an exception system like that. This is how errors should be done. This is another way of matching on results. Again, this is a little bit more elegant than the match statement, and this is sometimes the reason why we'll want an if-let binding rather than a match. Yeah?
In the previous slide, you said that this is how we should do errors, right?
Yeah.
But for example, now that file data is not okay, and I continue with it, so it might lead to some bugs. So isn't it better to like stop the program where we have?
So you'll have matched on file data, and if you try to operate on file data as if it's an actual string, the Rust type system will complain. Because file data is not of type string, it's of type result. Right. So if we ever want to do something with file data later, we'll want to match again, or maybe do some of the things we'll see later. If-let statements. And sometimes we will end up in a situation like this inside a function, and when we end up on the error variant, we'll want to return the error up, meaning our function returns a result too, yeah?
It seems like enum can substitute struct, so why do we have struct?
It seems like enum substitute structs.
It's like in Haskell, you always have data type name equals constructor and fuse. And here, so it's basically the same. You have enum type name and then constructor. So it seems like enum can substitute struct because a struct is just an enum with only one option.
Yes, kind of. But you could definitely get away with doing something like that. You wouldn't want to do it though, because the code that you end up with when you're trying to operate with this enum will have the enum name : and this one single variant. So look, I suppose, a little bit less pretty than you would if you're using normal structs. This duality between the whole sort of like data type system in Haskell and Rust is because structs and enums essentially build up an algebraic data type system. And so Rust have a way to essentially mimic, almost, the algebraic data type system that you see in Haskell.
Can I regard struct as a syntactic sugar of enum?
Not quite, because when you refer to a struct, you'll never refer to a struct by some name : the structure's name, unless you're taking it from a namespace. But you'll always refer to the struct by its name. You'll always refer to an enum variant by enum name : the variant name. But yeah, an enum with one variant and a struct are isomorphic. They are, yeah. So I just want to reiterate this. When we hit this error case, we returned the error. This happens a lot in Rust, because we'll have a lot of functions that return results because we want to keep this nice way of handling errors. There's a nicer way to do this, though, because this comes up so often. the question mark operator at the end of a statement essentially does the same thing we saw on the last slide. If this happens to be an error variant, it will shoot up and return the error early. Otherwise, we'll continue execution. File data is no longer of type result. It's now the type that OK would have had inside of it. So in this case, it's a string rather than a result string. These are iterators. If you think back to Haskell as well, very similar way of defining iterators, although they're not exactly the same thing. In this case, this is an iterator of all the natural numbers from 0 to positive infinity. The reason why this can sort of like fit in your machine's memory without exploding is because iterators are computed lazily. Possibly the most basic form of iterators are ranges. These are ranges between two numbers. This is 1 to 20, 20 exclusive, and this is 1 to 100, 100 exclusive. Here we test whether it contains 8. At the bottom, we sum all those numbers. This is the last thing we'll talk about this session. Just 1 second. Iterables can be used in for loops. At the top, there's an iterator from 0 to 10. In the middle, there's a vector, 1, 2, 10. We can iterate over that too. And at the bottom, we're iterating over all the characters of a string because the cars method on a string will return an iterator of all the characters in that string. Okay, time's up. I can feel Daniel eyeing me, and I can smell the pizza as well. You now know enough Rust to write your own programs. There are 2 key things I haven't talked about, and those are lifetimes and borrowing. Those I'll hopefully be talking about in the second session. There's a myth that these concepts are difficult. They are not, and I'll prove that to you next week. These are 2 links. This is a YouTube channel, and this is the blog post which I was heavily inspired by for this first session. Feel free to see those. And I'll take, oh, did you guys catch that, by the way? There we go. All good? And yeah, I'll take questions, any more questions that anybody might have now as well. Yeah, go on.
So when you say that Rust is lazy when it comes to ranges, like all ranges are open and closed?
Yes. So do you mean like closed ranges of numbers as well? They're also lazy? Yeah. Yes, 100%.
And only ranges are lazy or entire programming is lazy?
Any single thing that happens to be of iterator type is lazy.
And everything else is good?
Yes.
Are these slides available anywhere?
Good question. So I haven't published them anywhere now. However, I'll talk with Daniel. We'll get them published somewhere, and I'll make sure that you guys are aware. Any more questions?
The implicit returning on the last statement, if you put a semicolon at the end of that line, will it then not return?
It would return nothing, which is the unit type. And the Rust compiler would complain because the only thing that returns a unit type is a function that returns nothing, in essence.
So how does Rust compile either? It's like a union with a type or something?
Oh, that's an excellent question. I can't say I know the lower level details well enough to give you a confident answer about that. Okay, I'll hand off to Daniel now.